at 19 hours, and half an hour later we will go with the bus to Chania. The first 4 talks are all from Stockholm, and we will start with Matteo, who will talk about young massive star clumps in local high redshift galaxies analogs. Please.
Thank you. Good afternoon, everyone. My name is Matteo Messa, and I'm a PhD student at Stockholm University. And what I'm currently working on and what I will be presenting now is this study of young massive star clumps in the large sample, which is the sample of galaxies that Jens introduces this morning. And actually, these are snapshots of the 14 galaxies I'm using for this study. First of all, I think it's important to study clusters, and the reason is, even if we look at our name badge, what's on our name badge? There's a galaxy, but there are also lots of star clusters. Especially there's one which is very bright in the middle, and we know, and we've heard during these days that star cluster is where most of the ionizing radiation of the galaxy is produced, and it's because most of the very massive stars are in star clusters. And also they provide, they're the source of the strongest feedback in the galaxy. But we know that, especially when they form in a very dense region. So as we've been hearing for the conference, it's like the ionizing radiation has to push its way through, already at these small scales, through the clouds in order to escape from these small clouds, but then also go into the galaxy and then escape also from the galaxy, as we've seen, for example, this morning in ISO 338. What I think is not clear is why and how the presence of this UV bright clumpy star-forming region affects the possible escape of ionizing radiation. And this is what I want to discuss now, how and if the clumpiness in some way affects the escape of ionizing radiation from galaxies. And to give an idea of the scales I'm talking about, because star formation can be studied at very different scales, so from stellar to the galaxy one, there are 2 very important scales, and one is that of the star clusters, which usually is between 1 and 10 parsecs, which are bound structure. But then there are also clusters of clusters, what we typically call clumps, or even larger star-forming region, which span from 10 parsec to almost 1 kiloparsec. And what I'm studying with this sample, what I can resolve, this is an example of a galaxy. What we are seeing here are sources which have sizes between 10 and 10 parsec up to almost half a kiloparsec. So what we are studying are the scales of star cluster, but mainly most of the sources will be more complicated and extended clumps. Going briefly to the data analysis, so in each of the galaxies, I've extracted the sources using the source extractor, and then I've run photometry on each of the extracted sources. And in more detail, we have modeled each clump convolving the instrumental PSF with a Moffat profile, and this Moffat profile is where the size of the source is encoded. And we also added 1-degree polynomial background, and that's to account for more diffuse radiation we see, and that gives us the model of our observation. And then we have fitted each source in 5 bands at the same time, UV to optical. So keeping the same size in all bands, varying the fluxes. So what we get in the end for each source is one size and then the magnitude in these 5 bands. And then we have estimated uncertainty using Markov-Chain Monte Carlo technique. And in the end, what we have is almost 1,400 clumps, but only 600 have photometric error less than 0.3 magnitude in all these 5 bands. And this is the distribution of sizes of our sample. It's order in function of distance. So the top left, that's last one is the closest galaxy to us. And I want to point out that we cannot resolve all the sources. So there are some sources in each galaxy which are not resolved, and especially for the closest galaxy, so Lars 1, 2, 3, 4. That means they have sizes less than 10 parsecs. So those sources probably are actually real star clusters. But most of the sources we have are actually more extended than that, so they are what we call clumps. Here I'm showing in the histogram, there are both a shaded and a solid histogram. And the shaded is the total sample, the solid one is the one with low photometric errors. And also we see here that due to resolution effect, we have a shift of the median value of the sizes going from 50 parsec in the closest galaxy up to more than 100 parsec to the faraway galaxies. But in the end, what we have is a distribution of sizes that goes around between 10 and almost 600 parsecs. But most of the galaxies are smaller in radius than 100 parsecs. And to characterize them a little bit more, adding the magnitude information, what we have here is a size luminosity plot. What we see is that there's a relation, but there's also lots of scatter, and actually the scatter in this plot is the different densities that we are probing of the cluster. So for example, what we see in the top left, those are probably are very bright, but also very small, so they are probably superstar clusters. And we span a very wide range. If we compare that to what has been studied at higher redshift, so in the work of Livermore and collaborator 2015, they found a relation between the density of the clumps and the redshift, and here are, these lines are of fixed density, but at different redshifts. And what we see is that, yeah, most of our sources are where the redshift 0 clumps are, but then there are, our sample extend also to the density that have been observed in high redshift studies of clumps. And if we plot the sample using in the Livermore paper to derive this relation, we are probing like the same size and densities of the redshift 0 galaxies, and for the other samples, we are probing similar density, but at smaller scales. So we can resolve smaller scales, even if some of the high redshift clumps are from a study of lens galaxies, of course. And we're probing the at least the most dense of our sources are in the same space of the plot as this sample of dynamo sample, which is a sample of local galaxies, but very, highly star-forming galaxies. To put even more in the context, recent studies have been able to probe sizes of galaxies at very high redshifts, so from 3 to 8, but at very small scales. So, for example, I'm plotting two samples, the one of Bowens and the one of Van Zella. And what we see is that even these studies of galaxies, low luminosity galaxy, but what we see is that they are probing the same density that we are seeing in these in our samples. So it's like nowadays also at those redshifts, really, we are seeing the single compact star formation region, or single compact probably, or maybe proto-globular clusters. Now, moving to the results of the study of clumpiness in our galaxies, we have parameterized that in two different ways. And one is we have taken the total UV light in clumps and compared to the total UV light of each galaxy. And this is the way in what is shown in this plot in function of redshift. And the other one was focusing only on the brightest clumps. And what I've chosen here is to plot the median of the 5 brightest clumps for each galaxy, so actually the 3rd brightest clump. But I've also tried with the other measure, like the mean of those 5s, and the results I will be showing are similar in that case. What we see here is that our what we call clumpiness, so the fraction of light in clumps, is not set by the redshift, apart maybe from the last galaxy, so maybe from 12, 13, and 14. But for the other galaxy, it's not. And, but anyway, what I've decided to do is to exclude the last 14 in the following analysis, mainly because that's a galaxy that can be described by like one only very bright clump in the middle of the galaxy that makes almost 100% of the UV light. So it's not useful for the following analysis. We've tried to look for a correlation of the clumpiness with other galactic properties. We found a correlation if we plot the shear velocity over the dispersion velocity, what we see is that in dispersion-dominated galaxies, there's more clamp contribution. And this is also, it's sketched by this, we run a Sperman rank correlation test, and it seems to confirm this. And it is actually stronger here in the right plot, where we're not affected by like the brightest clamp of each galaxy that may be close to the center or maybe the center of the galaxy. And we have also tried, oh, I want to stress out maybe, this is similar to what has been observed in other studies, but usually other studies are, I mean, this study, in our study, the morphology are very different from like the thick disk galaxy that are usually seen at high redshift. So different morphology, but still the same correlation. And then we've tried to look correlation with, for example, star formation rate estimators, and we found a possible correlation with the specific star formation, but that's true only in the left plot. And so it seems like it's not both the star formation rate and the dynamic of the galaxy can contribute to affect the clumpiness. In particular, here I would like to show that the galaxies that have the highest specific star formation but low clumpiness, these are actually the galaxies which are rotation dominated, so not dispersion dominated. So it seems like dispersion dominated has a stronger effect on the clumpiness. And in the end, we've tried to look for correlation with the Lyman alpha, or at least, Lyman alpha properties. What we have found is that there's a tentative correlation with the escape fraction of Lyman alpha, in the sense that galaxies with higher escape fraction of Lyman alpha also have high contribution from clamps. It's not completely true the opposite, in the sense, for example, that there are some galaxies which have low escape fraction of Lyman alpha, but still they are very clumpy. And then we tried with other properties, for example, with equivalent width of Lyman alpha, but we didn't find any correlation with that. So, of course, as we've been hearing during the conference, it's not so easy to just relate Lyman alpha escape properties with one parameter. It's more complex than that. And also, still the sample is small, but we're increasing that. But still, it seems like we're starting to find a correlation. So, yeah, I would say the main conclusion of these works up to now are that we're observing clamps at very small scales, more than what's usually observed in high redshift galaxy, but which densities which can be as high as what is observed at high redshift. And that the clumpiness of these galaxies seems to depend on their, if they are dispersion dominated or rotation dominated, and also that higher Lyman alpha escape fraction seems to be related to a higher level of clumpiness. And one last slide about future work, because this is what we can find using photometry. But actually, we're also performing SED fitting to get ages and masses. So we have the distribution of age masses of the clamps, and also their distribution inside the galaxy, so where they are inside the galaxy, those clamps. So what we can do next actually is to derive what we expect as the ionizing budget of those galaxies, and then compare to what we see in narrowband observation of, for example, H alpha and Lyman alpha filters. So more results are to come very soon. Thanks.
Questions? Could you say anything about the clumpiness of the clumps? I mean, are they correlated, the positions in the galaxy?
Yeah, this is something we have not studied yet, but we can do. You mean the clustering of the clumps themselves? Yeah. Yeah. No, I haven't studied that yet. For sure, it's something interesting to do. We can run an analysis like that. Also because even by eye, I think it's in some cases it's clear that yeah, even clamps are clustered in some position. For example, well, maybe it's not easy to see from there, but in the brightest part of this galaxy has a collection of very high mass clamps. And I mean, it's clear that, of course, they are not distributed homogeneously in the galaxy, so that's something that can be done, but we have not results yet about that.
Okay. More questions? Okay, we thank you again. So the next speaker is Veronica Menaccio, who will talk about the escape of Lyman continuum radiation through galactic labyrinth in HAR11.
Okay. Hello, I am Veronica Menaccio, also a PhD student from Stockholm. I am going to present the escape of Lyman continuum radiation through galactic labyrinths in HAR11. So HAR11 is a small blue compact galaxy that is surrounded by a huge halo of ionized gas. It is a merger system, probably in the late state of the merger. Contrary to most BCGs, it has a very low neutral gas mass that is comparable with the ionized gas. This galaxy is a very well-known and very well-studied galaxy, mostly because it's the first galaxy where the Lyman continuum has been directly detected. And it's also a Lyman alpha emitter. Here, the Lyman alpha is in black contours. And it's a Swedish tradition, this galaxy. We are part of the third generation of students that are studying this galaxy. Starting with the Professor Berghalter, this is here the chairman. Okay, this galaxy is forming stars very efficiently and at high rate. 4 of 10 stars are forming inside of stellar cluster, making this galaxy a rich factory of stellar clusters. Adamo et al. Studied the stellar population, so the nuclear engineer from this galaxy, and found 200 stellar clusters with masses between 10 to the 4 to 10 to the 7, with a cluster age distribution that peak around 3.5 mega years. The star formation mostly happens at the center in 3 nodes, A, B, and C, and also a dusty arm. So node C has the older stellar cluster population with age in average of 10 mega years, while cluster B has the younger stellar population with an average of 3.5 mega years, and the dusty arms has a mixed population, but predominant the younger population. In total, from these 2 cluster detected, more than 50% are younger than 3.5 mega years. From the remaining, 40% are older but younger than 40 mega years. This is the age where the less massive stars explode as supernova. So that is very important because the most massive cluster produce a huge amount of very massive stars. These stars also produce a huge amount of ionizing photons, expanding the ionization structure of the galaxy. At the same time, also in these younger stars, the stellar winds inject energy in the surrounding media. By the older generation, they still contribute to the stellar feedback through supernova explosion. Summarizing, 90% or more than 90% of these stellar clusters are still actively contributing to the stellar feedback in this galaxy. So we are seeing HAR11 in a moment where the injected mechanical and radiative feedback feedback is at its maximum. The motivation is to study the ISM properties of the galaxy, the impact of stellar feedback, and also the connection to the Lyman continuum leakage, where these photons are leaking, how to study the mechanisms that facilitate this escape of these photons. So we have very deep Muse observations that we have corrected by stellar absorption. We have extracted some emission lines and resampled to 50 kilometers per second. Here we are interested in the H alpha and the O3 line. Finally, we have a result something like that. That is a velocity sliced H alpha and ionization map in winds of 50 kilometers per second in a velocity range from minus 400 kilometers to 350 kilometers per second. Now I will show you a movie that displays these results from minus 400 kilometers to 300 kilometers. So we start at minus 400, this is minus 300, minus 200, but please take a look at this structure here up at zero velocities, positive 150, 200, 300, and 350. So we clearly see several structures in these maps that change from a velocity winds to other velocity winds. Here I pick some of these velocity winds. Here on the top are at negative velocity winds, and here are at positive velocity. We see several structures, for example, arcs, a possible tidal tail, and probably a shell, and some filaments here in the south. But we are more interested here in this structure. This is an arc that extends around 180 degrees in the northern hemisphere, while at the south, at the basis of this structure, start to develop this a bunch of filaments that are at its maximum at central velocities. So we interpret that. It's very important also to point out this structure here. It is like a cavity, like a whole cavity that we are seeing through a window. So this point out, or this suggests that we are seeing a superbubble that powered by stellar winds or supernova explosions, and also helped by radiative feedback. So this superbubble has expanded, and at some point, due to instabilities at the south at negative velocities, it has fragmented. The gas inside, the interior hot gas, powered super or very high velocity stellar winds, dragging part of this shell outwards, and that is what we see as filaments here. And this is this is in agreement with simulation of this blow up of superbubbles. Continuing at central velocities, we see the largest structure in the galaxy. Here there is an arc, and here there is probably a tidal tail. The arcs are probably shaped by previous generation of massive stars, or they are shaped like the tidal tail by the dynamic of the merger. At positive velocities, there is more clumping. There are also filaments towards here, the north. And let's change. This is the ionization map. The ionization map shows an even larger number of structures. Most of this, or half of this structure, we don't see in the H alpha map. But to generalize, we see that here a halo that is fully ionized. We see also enhancement of this ionization in some regions. In negative velocities is this enhancement towards the south and southwest, while at positive velocities this enhancement is toward the west. These structures or highly enhancement are directly connected to one of the nodes or both nodes here, node A and node B, suggesting that these nodes are the source of these ionization photons that are working in the halo, ionizing the halo. So that is, in the talk of Göran already, he says that this part of the galaxy or this part of the halo has been found to be density bound, where Lyman continuum escape can escape. Knot B seems to be a very powerful source of ionizing photons. See, here at the basis of this knot start to form several, well, here is only one, channels, galactic channels of ionized gas. While we see other channels here towards the west and probably ones here at this direction. Knot C, although is one of the most massive, or is the most massive of the knot, it has no impact in the ISM because it is surrounded by a structure of low ionization, that we see this structure, that keeps the feedback of this knot local. So this knot has own super bubble that we can see here clearly, where the influence from this knot to the halo is not very strong. So finally, we have evidence of a fragmented superbubble that has created galactic channels where Lyman continuum can escape. This is only possible, or we only see that in this kind of map, in this method, slicing the velocity, slicing the lines. So, as conclusion is stellar feedback. Stellar feedback is very powerful in this galaxy. It has created superbubbles, ionization channels, filaments, arcs, and other structures. So Lyman continuum leakage, how? We already see it was due to this fragmented superbubble, or it has been powered by this fragmented superbubble, where very likely in the highly ionized regions. As Angela suggested, it's probably that it's leaking here in knot A, but also it's possible that it's leaking in these regions where the ionization is strong. And this is in agreement, somehow in agreement with Keenan that has presented a paper last year. So thank you very much.
Questions? Yes, Daniel.
Is there any relation between the existence of channels and the ages of the clusters, or the presence of supernovae, or not? Can you say what mechanism preferentially creates these channels?
That come from the superbubble, and for sure this superbubble has been powered by stellar winds and supernova explosions. So the generation from the stellar population is very, very young. It's very likely that it has been powered at most from stellar winds, but also helped by radiative energy. Not exclusively, but I think that at most by stellar winds, because of the generation of the stellar cluster.
More questions? I'm so amazed to see that the ages of the whole galaxy, more or less, is less than 3.5 mega years. I wonder how the coordination has worked. I just don't understand the mechanism. How can, and we've seen that in several cases. I mean, we have a rather large galaxy. And it seems to be synchronized in some way, that the burst occurs at different places at the same time. You have any idea why this? Because I mean the time scale for inflow, the accretion time scale is of the order of a few million years as well.
So in this case, this galaxy is a merger system. In mergers, they have an extra pressure due to the dynamic of the merger that trigger a stronger star formation. So
yeah, okay.
An extra
you mean that you reach the density peak where star formation can start?
Yes,
yeah,
that's trigger more star formation.
I guess so. Okay, thank you very much. So the next talk is by Lorenza Della Bruna, who will talk about the emerging phase of young star clusters, constraints for UV photon leakage in local galaxies.
Okay, good afternoon. My name is Lorenza Della Bruna, and I'm also a PhD student at Stockholm University. And as I said, today I will speak about my results on Lyman continuum photon leakage from H2 region in a nearby galaxy, NGC 7793. It is recognized that stellar feedback plays an essential role in regulating star formation in galaxies, and this feedback originates at small scale around young stars, and this shapes the region where the star formation occurs, as Ariane has showed this morning. But we know that then this feedback affects the entire life cycle of gas in galaxies, and indeed we observe outflows, galactic outflows, resulting from this stellar feedback. As we have heard yesterday, the most important source of stellar feedback are young massive stars. And these stars are preferentially born in young star clusters. So it is interesting to study what are the timescales for UV photons to escape young star clusters that are initially still embedded in their natal geomolecular clouds and then escape from the H2 region and into the galaxy. Today in particular I will speak about my preliminary result on the study of this galaxy. It is a flocculent spiral galaxy nearby at 3.4 megaparsec, and it has already been imaged with HST and ALMA. So here I'm showing the HST image and overlaid in green the contour of the ALMA coverage. And this has provided me with a sample of young star clusters and of giant molecular clouds that I can then use to compare to my data. But I've been working with recent Muse science verification data that I've been reducing. They are wide field mode and extended lambda coverage. And they are shown, the 2 pointings are shown in magenta here on the plot. So I will be very brief about the data reduction. So after performing the standard data reduction with the pipeline, I've been correcting for underlying stellar absorption using the PPXF software that also Peter Weibacher spoke about yesterday. So I will not go into detail about this. And once this provides us with a cube that only contains gas emission, and on this cube I then fit emission lines using Gaussian templates. And to do this I add up spatial region in order to get the minimum signal to noise in the weakest line of interest. And finally our obtained fluxes are corrected for reddening. We use PineApp that simply implements a Badner decrement. And what we obtain looks like this. So on the left is the H-alpha line map. And we can already see on the image, so I'm not sure if this works. We can already see by eye on the image, we can recognize many H2 regions, as well as many substructures of the H2 region. So we resolve individual peaks inside the regions. And we also see that the whole basically the entire field of view is permeated by diffuse gas emission. And if we look at the velocity distribution of the H-alpha line, we can see that the velocity changes across the field of view and also the velocity across the diffuse gas. In order to construct a sample of H2 region, we also use the package Astrodendro, the Python package that was mentioned yesterday, and what this package does is simply construct a tree that represents the hierarchy of structure in the data, and what one obtains is something that looks like this, with leaves that represent the single peaks in the data, and then branches that group some of these leaves. This is the H2 region sample that we obtain when we adopt this approach on the H-alpha flux. So in black I'm showing all the leaves detected by Astrodendro. But since we are resolving so many individual peaks, we are also interested in some branches that group some of these leaves. And on the right I'm showing the luminosity of each of these H2 region. We have adopted this approach not only on the H-alpha flux, but also on the H-alpha over S2 sample, over S2 line ratio. And this gives us a similar sample of H2 region. And when we look at where these regions are located on a BPT diagram, we see that, so these are the two samples of H2 regions selected on the two images. We see that they populate a similar area of the BPT diagram, but that when we select the H2 region based on the H-alpha over S2 flux ratio, we can exclude automatically some region that effectively lie outside of the ionization border, and these are the regions shown in white on the right side. Once we have obtained our sample of H2 region, we study the ionization structure of this region using ionization parameter mapping that was very well explained yesterday by Monica Relagna-Pastor. So essentially this uses the ratio of two ions that populates different regions of the nebula to study the optical thickness of the nebula. And here I'm showing a model that we have run with cloudy for conditions similar to our galaxy. This is for a cluster of 2 megayear, and we can clearly recognize that the region consists of 2 distinct zones, a highly ionized inner zone that is dominated by O3 and S3, and then a lower ionization envelope dominated by S2 and O2. And what we can then do is use this ratio of S2 over O3 to study where is the boundary between these two regions. And on the right here, I am showing one of the H2 regions in our sample. And we can see this is a classical ionization bound H2 region, where the inner zone is embedded in the region. Now, I apply this technique to a few of our H2 regions in the sample. I will show the result for regions. So first of all, we start with a young region. We see that on the top right plot, we have detected a few clusters with HST of the age 1 to 3 million years that are still partially embedded in the GMC. And in black, I am plotting the contours of the S2 over O3 line ratio, where this ratio becomes equal 0.5, and this is the fiducial limit that we take for the boundary between highly ionized inner zone and outer ionization envelope. And if we compare this with the plot on the top left, that shows the structure of the H2 region, we see that this O3 zone is still embedded in the region. So the H2 region is probably still ionization bound. And we can visualize this better by taking a radial slit through our data and looking at the radial trend of this ratio. And we can see that we are still above the optically thin limit on the site. And you can also see this by looking at S2 over H alpha that tracks the outer envelope and O3 over H alpha that tracks the inner zone. If we move to another young region, we can also here see that it is very well, the ionized inner zone is very well embedded in the H2 region. And again, if we take a radial cutout, we see something similar. And if we move then to an older region, which we can already see by the morphology, that is less regular. Here we detect a young star cluster with an age of 1 to 5 million years. And if we compare the contours of S2 over 3 to the region, already we can see that they confine with the boundary of the H2 region. So there is no transition between the highly ionized inner zone and the outside. And indeed, we can see it on the plot here. But this is more evident for this other region. And here we can clearly see that the inner ionized zone expands towards the north and reaches the boundary of the region. And what we get looks like this. So we clearly see that on one side of our slit, we are still below the optically thin limit, below the transition limit. And finally, I have looked at the fraction of DIG that we have in our data. And this is simply the ratio between the total flux in the H2 regions divided by the total flux outside the H2 region in H alpha. And we find a fraction of 0.6 if we take one of our two H2 region sample and 0.5 if we take the H alpha selected H2 region. And here we are leaving out the outliers of the BPT diagram that I've shown before. So this is not so surprising. This is in the range we would have expected. But what is maybe more interesting is to look at the distribution, so where these DIG spaxel are located on the BPT diagram. And it is often the case that even if the DIG is ionized by leaking H2 region, the ionization becomes harder by traveling through a high column density of gas. And we find a higher ratio of N2 over H alpha, for example, as Peter has shown yesterday. But in our case, it seems that almost all of the spatial points lie within the ionization boundary, and this is an indication, a strong indication that the DIG could be ionized effectively by leaking H2 region. So to conclude, we have used a sample of H2 region. We have analyzed a sample of H2 region and investigated their ionization structure with ionization parameter mapping, and we have found evidence for Lyman continuum leaking in at least 2 of the regions. What could be done next is a more qualitative estimate of the total escape fraction, and this is implemented in Pellegrini et al. 2012. So by assigning each H2 region an escape fraction based on the morphology of the region, we can compute the total escape luminosity of the H2 regions, and then find the escape fraction by summing up all of the escape luminosity over the total luminosity of the H2 region plus this escape luminosity. But if we want to be more quantitative and also investigate what is the role of young star cluster as source of DIG ionization, what we would like to do is something similar to what was presented yesterday by Peter. And this is comparing, since we have a sample of young star cluster, we can, through models, find what is the expected Lyman continuum luminosity emitted by this cluster, and then compare it with the luminosity that we observe, and that can be computed from the H alpha luminosity. And this is it. Thank you.
Questions? Yes.
When you and other observers study H2 regions in nearby galaxies, you seem to find most of the time very young H2 regions, less than 3 million years, where we think there would be no difference between binary stars and single stars. Now, if we are talking about binary stars and we think they are important contributors to the ionization budget, we should be able at some stage to find H2 regions where they provide a significant contribution, to which they provide significant contribution. So my question is, do you have a way to identify such regions, for example, which are 10 million years old? Of course, you have to see how you determine the ages, and can you find such regions in your sample, and how many are there, and so on? Or can you say something about this question?
Yes, so no, we have not yet investigated the ages of each region. The only thing we have done is to compare the distribution of youngster clusters that were detected, but this is something that I will think about doing. So you mean to have a sample of ages to see what is the distribution of ages?
Elisabeth? Yes. Yeah. There's one over there.
Timescales, sorry.
It's not activated. Try again.
Sorry, now we can discuss this at coffee. But timescales to open H2 regions and remove the gas are very short. Within 5 million years, 6, you don't see any more gas left around the cluster. So if you have a cluster of 10 million years, those photons are escaping into the ISM. There is nothing that is confining them close to the cluster. So I don't expect to see these regions.
Okay, thank you again. So the next speaker before coffee is Armin Rasek, who will talk about studying the Lyman alpha halo of Lars and E-Lars galaxies.
Okay. Yeah, my name is Armin. I'm a PhD student in the Stockholm University, and I'm very excited to give my first presentation in a conference about this astonishing topic, studying Lyman alpha halo of Lars and E-Lars galaxies. So I thought of starting my presentation by talking about some motivations which I thought can be relevant to this conference, which are studying the Lyman alpha study of local nearby galaxies. We know that it was more than 50 years ago that it was suggested that Lyman alpha emission line can be used as a tool to probe galaxies, in particular galaxies in high redshift universe. And indeed, in the past several decades, we have had some surveys to study galaxies, in particular galaxies in high redshift universe. And I think a good example can be actually the Muse study in 2017 by Florian Leclerc 2017. But something that was missing was studying the Lyman alpha halo size of the galaxies in the nearby universe. So on having a large sample, we were able to actually study this. And we were interested to look at the extension of the halo of these galaxies and also to see how much the halo of these galaxies contribute to the overall Lyman alpha luminosity that we measure for these galaxies. And also in a bigger picture, so having some understanding of galaxies in high redshift like MUs, and hopefully by the upcoming JWST even at further redshifts. And we can try to study the evolution of the Lyman alpha halo size of all these galaxies, having also some understanding of the nearby galaxies in the universe. So I thought of starting my talk by actually showing a very beautiful picture of one of our large galaxies here. So here, the blue line that you see is actually the halo of this galaxy, and you can see that actually how extended it is compared to the stellar radius that we have for this galaxy. What we have done for this study so far has been to actually look at the profiles of Lyman alpha, H alpha, and far UV. And we were using this critical star formation rate density of 0.1 solar mass per year per kiloparsec squared, which was used before in 2008 for Whirlpool galaxies by Vigil, if I pronounce correctly, 2008, and also in a paper that was published 2 months ago by Genevieva Micheva, 2018. So we were separating the profiles into halo and core. Maybe I should clarify first that this is actually this star formation rate density is the approximately where the slope of Kennecke-Schmidt law changes from efficient to inefficient. So basically what we are doing is to separate our profiles to inefficient star formation rate region, which we call halo, and efficient star formation rate region, which we call core. So having our profiles separated in these two regions, we were fitting a function, and here I talk about the exponential function that we have used with this form. And you can see that it has this amplitude times the exponential of minus r over the scale length. And here's an example. So if you can see it, I don't know how good the contrast is, but sure. But the darker color here actually is the core region, and the light color in the outer region is actually the halo. And these numbers here actually show the fitted scale lengths to these profiles here. And as you can see, as we would have expected from also previous studies, we can see that the halo scale length for the Lyman alpha, the blue color here, for halo is actually more extended than the core. So here is the result, the final result that we have had for our sample. So as you can see, the median size for halo is 2.48 kiloparsec, and for core is 1.45. So in other words, we can see that halos are more extended, which is something that had been also observed before in the high Z galaxies. So first, actually, by having these scale lengths, we were thinking of looking at the halo extension and also the core extension and see if there is any relation here. And as we can see, we don't see any correlation between these two scale lengths. And then next, we thought of actually looking at the halo fraction. And here you can, so the blue color here represents the halo fraction for our sample, and the red color here represents the mu sample. I need to stress here that the definition of halo fraction is different for our sample and the mu sample due to the nature of the studies that we have. if you are interested, we can, maybe I can talk about this if you have a question about the definition of the halo fractions here. But the main point here is that we can see that the Muse sample generally has a higher halo fraction compared to our halo fraction that we have measured for the large sample. So next, we thought of looking at the halo fraction and the halo scale lengths. So we know from previous studies that we might have expected that there is some correlation between the halo fraction and the extension of halo. And here we can see that indeed, for galaxies that have higher halo fractions, we have actually more extended halo. Then we thought of exploring our sample more and actually look at some parameters like Lyman alpha equivalent width and escape fractions, and to look for any possible correlations between halo fraction and these parameters. But as you can see from the plots here, we don't see any correlation between halo fraction and Lyman alpha equivalent width or the Lyman alpha escape fraction. And then we try to extend this also to looking at the total Lyman alpha luminosity and also the nebular extension. So one might have expected that actually if the halo fraction is higher, maybe for galaxies that have higher Lyman alpha luminosity, maybe the halo fraction is higher, which we cannot conclude from our data. Or also we know that actually the dust destroys the Lyman alpha photons. So in principle, for galaxies that are dustier, we might have expected to have maybe less halo fraction. But here you can see that we don't see any anti-correlation between the halo fraction and the nebular extension in our data. What we did next was actually to convolve our images with the musing up to redshift 3 and see how our galaxies look like. And maybe we can compare our sample with the Muse sample. So for that, first we, like using the Muse recipe, we were actually looking at the non-convolved far UV profiles, and we were fitting an exponential and measuring the scale lengths for our galaxies, and then having that, convolving it with this Muse seeing up to redshift 3, and adding another term for the halo. We were measuring the Lyman alpha. We were fitting to Lyman alpha profiles, and then this is what we found. So for those galaxies that we found non-zero halo fraction, we found that the scale length for the continuum is quite similar to the Muse sample. However, for the halo size, we found that the Muse sample has a higher scale length, or their galaxies are actually more extended. This can be because of different sample selection, or this can be also because of the small field of view that we have for large galaxies, and after the convolution, maybe we cannot measure all of the Lyman alpha luminosities that we have for the convolved large sample. But then we were thinking of looking at the extension of halo versus extension of the continuum, and we found that actually in terms of covering the halo extension and also the continuum extension, our galaxies more or less cover the same range like the Muse sample. So to conclude, we have found that the galaxies that are more extended have higher halo fractions. We could not find any correlation or anti-correlation in the large sample between halo fraction and Lyman alpha equivalent with escape fraction, total Lyman alpha luminosity, and then also convolving our galaxies to redshift 3, we found that the Muse, they are not as extended as the Muse sample. Thank you.
Yes, Daniel.
There are some large fraction of Lars and E-Lars which have been observed with H1. Did you try to find any correlation between H1 and halo?
We have not looked at the H1 and the halo. I mean, this is still a work in progress. We have not finished our studies yet, but that's something that we have not explored yet.
Lutz?
Yeah, so you say in your first point in the conclusions, as expected, higher halo fractions give more extended Lyman alpha halos, but this is not what we see in the Muse data. There, the halo fraction is totally uncorrelated with the scale length of the halo, and I'll show that again tomorrow. But just so you may say, as expected, we may have expected that for Muse, but we don't see any of that.
Sure. Maybe I can just actually just comment on it. So I was actually trying to be careful about this, and that's why I didn't write we find any correlation. I just wrote that for galaxies that we have high halo fractions, we see that also they are more extended. But this is not a strong correlation between the between these two parameters.
Yeah.
In the beginning, you showed also the H alpha scale length, right? Did you correlate? Did you have a plot correlating the two scale lengths, the Lyman alpha and the H alpha?
To look for
the scale length of the H alpha halo and the Lyman alpha halo. No.
Not yet.
Okay. Short second question. When you say this, that Muse halos are more extended, did you statistically quantify that? Because your sample size is quite small, right?
No, I was just, so what we have done so far is just to actually, I mean, this, basically, Okay. No, we were just, so I was just curious to look at the median of the core scale lengths and the halo scale lengths, and just maybe a very simple comparison between our sample and the Muse sample.
Okay, let's thank the speaker then. So we'll break here for coffee and we'll be back at 5:30.